So in this question, we're asked to find the volume of a solid revolution given the following functions. We're given f of x equals e to the x over 2 plus e to the negative x over 2, which looks a little scary, but it's not nearly as bad as it looks at first glance. We have g of x equals 0, and this is nice, h of y equals -1, and j of y equals 2. And all of these functions, the area between these functions rotated around the line y equals 0, and this is just the x-axis here. So to start, as with any solid revolution question, we need to find the method that we are going to be using to solve this. If we look, we have our axis of revolution in terms of y equals some value, some horizontal line here, and then we have two functions, f of x and g of x, defined in terms of x. So we have our axis of revolution in one variable and two functions in the other, and we can, if we look here, if we have two functions in one variable and our axis of revolution in the other, we can use the disk method to solve for this. So we can use the disk method here, and to start that, we need to find a domain. Whether we're using the disk method or the shell method, we would need to find a domain. We do that by setting these two functions equal to one another and finding where they cross. If we do that, if we set e to the x over 2 plus e to the negative x over 2 equals 0, then we can say that e to the x over 2 plus 1 over e to the x over 2, because that's what this negative here does, is 1 over this, equals 0. From here, we can find a common denominator in e to the x over 2. So if we do that, then we multiply this term by e to the x over 2. If we do that, because they have the same base, we add exponents. When you multiply, you add exponents if they have the same base. And if we add x over 2 plus x over 2, that's 2x over 2, and then the 2's cancel, leaving us with just x. So we have e to the x plus 1, which is this one right here, over e to the x over 2. From here, the reason we found this is now we can multiply it out. We can multiply both sides by e to the x over 2, which 0 times e to the x over 2 is just 0, because 0 times any value is 0, leaving us this numerator here, e to the x plus 1 equals 0. And from here, it's fairly simple. We can subtract 1 over and take the natural logarithm of both sides to get x equals the natural logarithm of -1. And this statement is never true, because the natural logarithm of -1 doesn't exist, because you can't take the natural logarithm of a negative number. And so, because this statement is never true, these two functions never cross one another. And because they never cross one another, we need to look elsewhere for our the bounds for our domain. And if we look, we have these two other functions here, h of y and j of y, which will serve as bounds for our domain. So we can write, if h of y equals -1, well, that's the same thing as saying x equals -1, and the same thing with j of y equals 2, x equals 2. And so now we have -1 and 2 to serve as the bounds for our domain here. So if we write this, we have x is between, x is a member of, -1 and 2 inclusive. And so, as always, we need to choose a test point. And we choose a test point so that we can evaluate both of these functions at that point and find which function is greater during this interval. And so if we choose a test point between -1 and 2, but not including -1 or 2, then we can choose 0, because 0 is the easiest number to evaluate for here. So if we say f of c, so f evaluated at c equals 0, then we can say e to the 0, because it's x, we look, it's x over 2, and if we plug in 0 here, it's e to the 0 over 2, and that's just 0. So if we say e to the 0 plus e to the -0, and -0 doesn't actually change the value of this, because there's no such thing as -0, because -1 times 0 is just 0. So we're saying e to the 0 plus e to the 0, essentially, and e to the 0 is just 1, because any value to the 0 is just 1. So we have 1 plus 1 equals 2. And then we have g of c, well, that's just equal to 0, because g of any value x equals 0, because g of x equals 0. So now we can say that our f of c is greater than our g of c, because 2 is greater than 0. This is a completely true statement. And now from here we can widen this to say f of x is greater than g of x is greater than or equal to our axis of revolution value. Our axis of revolution value, if we look, is 0 here, y equals 0. And so, And so we can set up this inequality where f of x is greater than g of x is greater than or equal to, in this case it is equal to, our axis of revolution. Over this interval, -1 is less than x is less than 2. because we're using the disk method, what we need to do now is we need to find our two R functions, our capital R of x and our lowercase r of x. And the way we do this is we find which, we take the function which is farther from our axis of revolution in this inequality. That's the reason we set up this inequality like we did. Find the function that is farther from it and subtract our axis of revolution value. So we have f of x is farther from this minus our axis of revolution value, which again is just 0. It will leave us with just our f of x value here, which is e to the x over 2 plus e to the negative x over 2. And for our lowercase r of x, well, that's just the closer function minus our axis of revolution. So we have our closer function, which is g of x, and g of x equals 0, minus our axis of revolution value, which is also 0. We have 0 minus 0 just equals 0. And so with these two functions, we're ready to set up our formula and evaluate this. So now that we have our two r functions, we can go ahead and write the disk method formula here, which is pi times the definite integral from -1 to 2 of our outer function capital R squared minus our inner function lowercase r squared dx. And from here, I'm just going to substitute in what we just found to be our r function. So our capital R of x was just e to the x over 2 plus e to the negative x over 2, and we square that. Then our lowercase r of x was just 0. So this 0 squared is just going to disappear in the next step because it doesn't actually contribute to the value of this expression. And so what we need to do now is we need to square this binomial out. And to square a binomial, you square the first term, multiply the two terms together and double, and then square the second term. So if we square the first term, e to the x over 2 squared is just e to the x. And if we multiply these two terms together, e to the x over 2 times e to the negative x over 2, we need to add exponents here. So x over 2 minus x over 2 is 0. So we're left with e to the 0, which is just 1, and then we double. So we have 1 doubled is 2. And then we square the second term here, so e to the negative x over 2 squared is e to the negative x, e to the negative x. And then we still have our dx, and we are ready to integrate because there's nothing more we can do here. And so from here, the integral of e to the x is just e to the x because the derivative of the exponent is 1. So now we have 2, integral of 2 is 2x, and then we have the integral of e to the negative x, and that's negative e to the negative x because the derivative of negative x is -1. So we multiply by, or divide by -1 to get negative e to the negative x. And from here, I rewrote this e to the negative x, I rewrote that as 1 over e to the x. And this is the same thing here, and that's all I did in that step. And I did that because I want to find a common denominator here. And you don't have to do this. You could, of course, just go ahead and plug in numbers immediately after you integrate. But I like to simplify before I do any of this. So I'm going to find a common denominator here. If we find a common denominator, our common denominator is e to the x. And so to do this, we multiply both of these terms by e to the x. So e to the x times e to the x is e to the 2x. You add exponents. And then here, 2x times e to the x is just 2x e to the x. And you have -1 over e to the x, evaluated from -1 to 2 times pi. So from here, there's nothing more we can do, so I'm going to plug in some numbers. If we plug in 2 here, we get e to the 2 times 2, plus 2 times 2 times e to the 2, so e squared, -1 over e squared, so this term here. And then we subtract this evaluated at -1, so if we evaluate this at -1, e to the 2 times -1 is just e to the -2, plus 2 times -1 is -2, so it's going to be minus 2e to the -1 minus 1 over e to the -1 here. And from here, what I want to do is I want to find another common denominator, and the common denominator here is e squared. And so to do this, to get this over e squared, I need to multiply by e cubed because we add exponents, and the difference between 2 and -1 is 3. So I need to multiply this term by e cubed. So if I do that, -2 plus 3 is 1. -1 plus 3 is 2. And this is the same thing as e to the 0 plus 3 is 3. So I'm left with e to the first, so this is just e, minus 2e squared minus e cubed over e squared. Now I have a common denominator. I can put them over the same denominator here. So I can distribute this negative. So I have e to the fourth plus 4e squared minus 1 minus e to the first plus 2e squared plus e cubed. That's what I did here. And now the only thing left to do would be to, rearrange our the numbers in our numerator in order of decreasing exponent and to combine like terms. So if we do that, we have e to the fourth plus e cubed plus 4e squared plus 2e squared is plus 6e squared minus e minus 1 over e squared. And this is all we can do to this function. It still looks kind of gross, but this is as good as we can get it. And if you wanted to find some value, oh, and of times pi, of course, this pi has been hanging out front this entire time, so it's still times this expression, obviously. But if you were to evaluate this at, put it into a calculator and evaluate it, you would get this number approximately, our volume is approximately equal to 49.022. So this crazy number here is the volume of the solid of revolution generated by rotating the area between these graphs around our x-axis.